they try to compute a joint function of their inputs in an interactive fashion, and the quantity that we're interested in is the number of bits they exchange. And you can take that the parties have access to a public random tape, and each of them have access to private randomness. Good. And the inputs are drawn from some distribution that is known to both players beforehand. Okay. And I would like to associate a notion of information cost to these protocols. And in this case, I really want to associate a number to each of the players and want to look at them differently. For instance, I want to say that the amount of information that Alice reveals in the protocol is exactly equal to the mutual information between her input and the message of the protocol, conditioned on Bob's input and the public randomness. And in a similar fashion, you can talk about the amount of information that Bob reveals. And the total information is the sum of these two quantities, but I want to look at these quantities, as I said, differently. Okay, and not look at the sum at one go. Good. Okay, having defined the model and the notion of information, I think ready to state the question. So one natural question and a beautiful question to ask is, say, given a protocol with some information and communication, can you always simulate the protocol? Can you come up with an alternate protocol that simulates the original protocol with just order information bits? And say if you cannot do that, then the next question is, what is the best simulation that one can come up with as a function of the communication and the information of the original protocol? Okay, good. And this question has been well studied, and BBCR gives a compression to square root of the product of the communication and the information, or they give a simulation which compresses the protocol to square root IC bits of communication. And in the same paper, they show another compression for another compression to I times log square C, where when the inputs are drawn from product distribution. And later, Brehm and Rao showed another compression to order of information plus the number of rounds of the protocol. And this is the result that we'll use in one of our compressions here, part of the compression. And also, Braverman gave another compression which just depends on the amount of information in the original protocol, which is namely 2 to the order I. And recently, GKR showed that this is tight. And we did see this separation in this workshop. This is essentially the exponential separation paper, which shows that 2 to the order I is tight. And you cannot do any better if you're just looking for a compression just in terms of the information of the original protocol. Okay, but this does not rule out maybe something like I times log C or I plus log C or some dependence on communication. The question is still open. So good. So in this work, we showed 2 compressions. One where we get a compression to order IA, which is nothing but the information revealed by Alice, plus C to the 3/4 times IB to the 1/4. Okay, and another simulation gives compression to IA times 2 to the order IB. So earlier, the other compression that I mentioned was something like 2 to the order I, but here you were able to get one of the terms outside. Like you can separate these, but okay. Let's see where these compressions are good, or are better than the previously known ones. So if you look at the case where the information revealed by Alice is like really large, and the information revealed by Bob is like small, in this case you get a compression that's better than BBCR. The good thing here is like you're able to have a dependence on the information, and it's independent of the communication term there. So yeah. And the second compression actually says if one of the parties reveals only constant amount of information, then you get optimal compressions, something like to order I. Okay. And in this talk, I'm just going to be, I'll describe the protocol or the simulation that achieves the first compression. So I won't have time to talk about the second compression. And as you would have seen, we gain mileage when the information is really asymmetric. Like one party reveals a lot of information, and the other party reveals very little information. That's a setting where we gain some mileage. Okay, and this is something which we encounter when we study data structures, and let's try to understand why that's the case. Okay, so we say, okay, the data structure problem is as follows. You have some input, and you are required to pre-process the input and store it in a very succinct fashion. At the same time, you would want to retrieve data or information from it in a very quick fashion, okay, or an efficient fashion. So, say you have a database, or okay, what is the problem? So you're given a query, and the query algorithm is going to probe some cells in the memory for information, and ultimately it makes T queries and would like to answer the question. Okay, so and if you observe, every query algorithm now can be simulated by a communication protocol where Alice receives the query and Bob receives the data structure. Okay, and depending on the parameters, say something like the size of the data structure and the cell size of the amount of bits that each cell in the memory stores, which we call W here, the word size, the protocols are asymmetric. Okay, and an example question, a problem that you encounter in the asymmetric setting is this question of lopsided set disjointness, where again Alice and Bob receive two sets, and their goal is to find out if the sets intersect. But here you impose a restriction on the size of the set that Alice receives, which is here you set it to some parameter k, and the size of the universe is k times n. But you don't have any restrictions on the size of the set that Bob receives. And optimal lower bounds for this was shown by Petrascu. And this problem is very important in the data structure regime, because this was a central problem which was reduced to many other data structure problems and gave very good lower bounds. So I won't get into that, but I probably would spend more time on the compression, and yeah. Good. So before I show you the compression, let's just understand this notion of the communication tree of a protocol. So it's a rooted binary tree where every node belongs to either Alice or Bob, and fixing both their inputs and the public randomness, there's a distribution that's induced on the leaves of the tree. Okay, and a particular run of the protocol corresponds to a path from the root to the leaf. Okay, and every edge here that I've colored red is owned by Alice. By that I mean, in the protocol, this particular message was sent by Alice, and everything that's colored purple here belongs to Bob. And to every node, you can associate a distribution, which is the probability of the next message being sent conditioned on the previous transcript and one of the party's inputs and the public randomness. Okay. So let's keep these. We'll probably use these distributions, or like the protocol itself induces the distribution, and we'll use it later in analyzing some parameters of the compression. Good. So now I'm in a position to explain the compression. So let me first give you a high-level picture of how the compression is going to look, and then get to the details. Okay. So I'm going to do the compression in two stages. In the first stage, I'm going to convert the given protocol into a bounded round protocol. And the protocol is going to look like this. So okay, before I describe that, the intuitions should be clear. Let's take that Alice is the party who learns less information, or Bob is the one who reveals very little information in the protocol. And so Alice now tries to guess k bits of the transcript. Okay, and I'll make it very clear as to what I mean by guess and so on. But and then she's going to send this transcript across to Bob, and then Bob's going to verify if she's made any mistake in the guess or in one of the messages that she has sent that corresponds to Bob in the original protocol. And then he's going to point out the mistake, and Alice is going to correct the mistake and then continue with her guess. And they're going to do that until they hit a leaf of the protocol. And then, so once you have a bounded round protocol, we're going to apply this simulation from Brame and Rao, which tells us that if you have a protocol with information I and number of rounds being R, you can compress it to or simulate it using order I plus R communication. And so for doing this, we need good upper bounds on the information and the number of rounds of the protocol, or the bounded round protocol that I'm going to describe. Okay, good. Good. So let me describe the protocol to you. So now let's fix a parameter k, which I'll set it later at the end, but and let that be the number of bits sent by Alice in every round. And we're going to use some extra public randomness, these numbers rho, which are between 0 and 1. Good. So now starting from the root, Alice is going to guess a path of length k, but then I haven't told you how she's going to sample this yet. So let me first tell you what these colors mean on these edges. So the red edges are the ones that correspond to Alice's message in the original protocol, and the yellow edges are the ones that correspond to Bob's message in the original protocol. And all these red edges are sampled privately as she had done it in the original protocol, but now she's going to do something different for these yellow edges. And for these yellow edges, she's going to use public randomness, and she's going to have a guess on the probability that the message is 1, condition on her input, and public randomness and the previous messages. And if rho falls somewhere in between 0 and this guess, she's going to send a 1, otherwise a 0. So in this case, she sends a 1 because rho falls in some range. Good. And she does it for the rest of the protocol. Sorry, the rest of the edges. Good. And now she's going to send this across. And now Bob has to verify if these yellow edges have been sampled correctly. Okay. And he has a disagreement if he would have sampled the other edge. Like with every node, you associate two edges, either a message being a 1 or a 0. So here in this particular case, Bob has a disagreement because the according to using rho 4, he would have sampled a 1 instead of a 0 in the original protocol. Okay, and now he's going to send the position of the mistake, the first mistake. She could have made many mistakes, but he's just going to identify the first mistake and going to send the position across. And Alice is going to correct the bit and then go down, guess another k bits. Okay, and they're going to do that until they hit a leaf. Okay, so is the protocol clear? Or anything? Okay, good. Great. So let's make this small observation. So a mistake is made when this number rho falls in between the actual probability and the guess probability. So this was the actual probability that Bob sending a message 1 conditioned on the previous messages. and Alice's guess is so. There's a mistake exactly when row falls in between. So we'll use it later in the analysis, but we shall keep that in the background. Okay. Good. So having described the protocol, I am left with 3 tasks or 2 tasks. 1, I have to show that the number of rounds is bounded. 2, I have to show that the information is bounded. Okay. The first observation that you can make is the expected number of rounds is upper bounded by C over K plus the expected number of mistakes. Okay. By here C, I refer to the communication of the original protocol that's given to us. And to observe this, every round in the protocol either has a mistake or has no mistake. So you require C over K rounds to actually send all the messages of the original protocol, and taking every round with a mistake, as wide, you get an upper bound of C over K plus expected number of mistakes. Okay. Good. So now, to bound the expected number of rounds, I just have to bound the expected number of mistakes. So to do that, let's recall that we had a mistake when the public the numbers chosen publicly, a row falls in between the actual probability and the guess probability. So this tells you that the probability of making a mistake at a position I is equal to the L1 distance between these 2 distributions. And by Pinsker, you can show that it's upper bounded by the square root of the information of the ith bit in the original protocol. Good. And now an application of Cauchy-Schwarz and chain rule for mutual information tells you that you have the expected number of mistakes to be at most square root of C times IB. The good thing is you don't have dependence on IA here, something that you would expect before doing the analysis. So I'm left with the task of bounding the information of this protocol. Let me first do the easy part, where I'm going to upper bound the information that's learned by Alice. So in every round, Bob speaks the position of the mistake, which is exactly a log k bit vector. So the information learned is at most log k, and therefore the total amount of information learned is log k times the expected number of rounds, which is this quantity. So now let's upper bound the information that Bob learns. It's a little tricky. So okay, so let's look at one single round of the protocol for now, and say the mistake was made at some index j. And so in the final protocol, or in the simulation, we discard all these messages that occur after j. Okay, and these bits correspond to at most k bits of information to Bob. And now we are left with the task of analyzing the amount of information that Bob learns in the messages that are not discarded. Okay, and the messages that don't get discarded, they either, if you look at each of these messages, each of these bits, they either correspond to Alice's message in the original protocol or Bob's message in the original protocol. So we can upper bound the information that Bob learns from any message that correspond to Alice in the original protocol by the information that he learns in the given protocol. But now it's but it's not clear if how much of information that does Alice reveal about the messages that she guesses right. Okay, So the question that we want to ask is, like, does the bits guessed by Alice, reveal any extra information to Bob? And it looks like it does. And I'll use this tie lemma for the analysis, but I won't get into the proof of this. So what this says is, say you're given a protocol in which Bob speaks 1 bit with information epsilon, and you run this guess protocol, you would be able to show that the amount of information that Bob learns in this case is upper bounded by the square root of epsilon. Okay. So in a way it tells you that each of these bits reveal at most square root of the information that Bob would have revealed to Alice in that particular step. Okay. Good. So using this lemma, what you can show is the information learned by Bob in the messages that from the messages that did not get thrown away is upper bounded by IA plus square root of IB times C with a log factor there. I mean, let me just, okay, so IA is exactly the contribution from the messages that, the contribution that comes from the messages that correspond to Alice's original message or message in the original protocol. And using this lemma, you again do a Cauchy-Schwarz and chain rule for information to get the square root CIB here. And the log C is a technical issue, so let me not get into it. Okay. And then for all the discarded messages, you know that information learned by Bob is at most k times the expected number of mistakes. Okay. This tells you that the total information learned is upper bounded by this number.
Good question.
Yeah.
Toy lemma tight?
Yes, I'll show you an example. Okay. So before I show the example, let's first wrap it up. And how much time do we have? Okay. Okay. So now you set k to be something like c to the 1/4 and ib to the power minus 1/4, and you get that your new simulation has number of rounds bounded by c to the 3/4 and ib to the power 1/4. And information, actually, you don't really have to worry about all these terms. Just worry about the IA and this term. Okay. It's just by setting k to be that number on these, you just get the values. Okay. Good. And now, given this, you just apply the simulation from Raymond and Rao, which gives you something like order I plus r, which is exactly this number. And k was chosen in such a way that the information and the number of rounds are made equal. Okay, this completes the proof of the simulation. So now, before I wrap up, I'll just show you an example where this lemma is tight. So Alice gets a number which is either half minus epsilon or half plus epsilon, and Bob gets a number which is either half minus 2 epsilon or half plus 2 epsilon. And now let me describe a distribution on both their inputs. So Alice either gets half minus epsilon or half plus epsilon and pick one at random with probability half. And then after fixing x, Bob either gets half or half plus 2 epsilon, essentially the numbers that are epsilon away on the line. And you pick one at random from them. And the protocol is the following. Bob sends 0 with probability y. Okay. Y is a number from between 0 and 1. In this particular protocol, Bob exactly reveals something like order epsilon squared bits of information. Now let's look at what the guess protocol does. So Alice's best guess would be her input x, and she's going to have access to a public random string, a numbered row sampled publicly, and she's going to send a 0 if a row falls in between 0 and x, or she's going to send a 1 otherwise. And in this case, you want to show that they reveal approximately something like order epsilon bits of information. That's because say y was half, and if rho falls somewhere in between half minus epsilon and half, that's exactly the case where Alice gets to know that x could not have been half minus epsilon. That's like one bit of information there. So I'll just end by some open problems. So the first thing to understand would be to see if you can actually compress it to IA plus c to the square root of actually IC and IB. Because here we get something like c to the 3/4 and IB to the 1/4. This would improve parameters. Another very interesting problem would be to see, just looking at the regime where IB is upper bounded by log c, can you compress it to like IA plus poly log c or IA times poly log c? These would be very nice, but probably a first step would be to maybe show this, or maybe not jump directly to this, but yeah. Thank you.
Thank you.